Hey guys, today I'm going to talk about model rocketry a bit. So I'm going to start off today's video by showing you this rocket. So this is a rocket that my team and I made for the University Student Launch Initiative. It is about 10 feet long, 6 inches in diameter, and it weighs about 63 pounds. It has a couple separation points. So right here next to her here is a coupler, which separates on both sides. And this here at the nose cone, it also separates on both sides. So this is going to be important for what we're doing today because I'm going to show you this Matlab code that I made and walk you through this code. So like I said, this is Matlab. So Matlab is coded in C. It's relatively similar to Python, but it's a little complicated. So if you are new to Matlab, I would suggest checking out some tutorials and doing some more basic coding before you jump into this code because it's relatively complicated. Matlab is something that you can get just as a single user. You don't need to be associated with an institution. I think it's like $145 for a lifetime subscription to Matlab, and it can do some really powerful things. So I would really recommend looking into it if this is something that you would like to do. So what this code does for the competition that we were in, there were several requirements. Main ones were that we had a descent time. So from the apogee to ground, it had to be under 90 seconds. We had a drift radius had to be no more than 2,500 feet. And the kinetic energy at landing had to be less than 75 foot-pounds. So this code takes the specific weights of all of the sections of the rocket and it calculates all of those values for us. So I'm just going to walk you through this code and how I made it so that you guys can implement it to use with your unique hobby rocketry if you want to keep track of that kind of thing. So first off, it's always a good idea to label your code and have a last updated just so that you know how up to date your code is and you can keep track of the versions of your code. And then of course the clear CLC and clear figures. This code has a lot of figures which you'll see at the end, but that's why we really want to make sure we're clearing them after each one. So, and then we'll get into the knowns here. So first off, the coefficient of drag of a torsional parachute and the coefficient of drag of an elliptical parachute. These are known values. They're usually, you get them with the supplier of your parachutes. They will tell you them. So I'm going to go back to this photo really quick. So this rocket actually has a total of 5 parachutes. So there's 2 parachutes for the aft section, which separates on the fore side of the coupler. So it's got a drogue here and a main in this section. And then the fore section, which includes this piece of body tube and the nose cone, has got a main and a drogue that share a bay in here. The rocket also has a payload, which is, it shares a bay with the main chute for the fore section. And then that payload has its own parachute that deploys with the main chute. So, but I wanted to make sure that you guys understand, where our parachutes are and stuff like that. So all rockets are different. So that's important to note. If you are wanting to use a code like this, just make sure that you're changing things for whatever the specifics of your rocket are. And if you have any problems trying to, figuring out how to modify this code for the specifics of whatever you're doing with your rockets, you guys are totally shoot me a comment and I will reply as best I can. So getting back here, so the coefficients of drag, like I said, those will be supplied by the manufacturer of your parachutes. Just note that those are not always accurate. So if you actually test the coefficient of drag of your parachutes, which I would encourage you to do, you're likely to find that the coefficient of drag is not the value that you're given. But for the purposes here, we did treat it as if that is the value that they were. So we used the given values instead of our calculated values for all of the code here. And that's what I would encourage you to do.
So, and then of course your acceleration due to gravity. I am using Imperial Units. So since all of the requirements that we were given were in Imperial, we just kept everything in Imperial. Though I completely understand if you want to move over to metric, as it is a little bit easier sometimes. So you want to have the weight of all of your sections. So we've got weight and mass. So we made it even more detailed because we wanted to see if there was a significant difference of the velocities that were reached and the descent times that were made under just the drogues, because the weights change a little bit after the main parachute, because after the main, the weight of the main parachute is not affecting the weight of the full body because it's deployed. So that's the difference between this weight after main and this weight between main and drogue. And then we had 4 sections, right? The 4-section nose cone, aft section, and coupler, which of course the 4-section nose cone are tethered to each other and the aft section and coupler are tethered to each other. But since they would all have different kinetic energies, since that's based on, the individual mass of each section, we did have to do it all separately. So, and then down here we just calculate mass, just take the weight and divide it by gravity. We also had a payload, so we also calculated the kinetic energy at landing of the payload and how long it'll take to get to the ground of the payload. So now down here, this is the altitude that we set our main deployment to happen at. This is something that we set in our altimeters. So we used a delay switch, since the altimeters that we were using were RRC3s, and they actually have, you can only set per 100 feet, but we ended up needing that 50 feet to stay within our requirements. And so we had a little delay switch in there. So this is the height that the payload was supposed to deploy at, and then the height of the drogue parachute. So this is supposed to be when our apogee was. This was our target, but it's all about when you actually reach that target. So because we don't really control when the drogue parachute comes out. It comes out right after apogee, wherever apogee ends up being. So these minimum speeds here are just the off the rail velocity. So there also was a requirement of the competition, was that we had to have a minimum speed off the rail. So, and then of course the kinetic energy, the maximum allowable kinetic energy. So for our calculations, so first we're going to do the maximum velocity of each section. So this is just the kinetic energy times 2 divided by the mass of each section to find the velocity, and then the square root of that. So this just calculates what the maximum velocity is at any one point. Since we use the density of air a lot, this function here takes the density of air, since it changes significantly from 0 to 4,000 feet, and we actually launched in like a high desert, and so it's much higher. We started at about 4,000 feet, so the density of air changed significantly in that amount of time. So this is just a function that just takes the density of air as it changes with altitude. But this is a very helpful function here, and then it just spits you out a value for rho, your density of air, that you can use later on as a function. So like here I have rho at the height of the main parachute, which is the value that I defined earlier up here. So now we want the main parachute area. So this actually is a function. So it's all of the ranges of parachute I could use. So this is how we decided what size parachute to use. we hadn't actually, the purpose of this code was to also help decide the size of the parachute that will keep us within all of those requirements. So this code it has using a 60-inch to 144-inch, 5 feet to 12 feet is the range that we used. I believe we ended up going with a 1 6-foot and 1 7-foot parachute, if I remember correctly, but we'll run the code at the end and show it again. So, so this is just a function for main parachute area. Our main parachutes were toroidal, so this is a function for the area of a toroidal parachute. And then the area of the actual main, or of the fore parachute and of the aft parachute, was changing because of the size of the actual parachute. So, and then based on that area and what the velocity is of the fore section and of the aft section as one big unit. So that's the fore section plus the nose cone, and the aft section plus the coupler is what these velocities are. So we had to calculate descent times. So descent time is actually relatively easy to calculate. It's just the height of the main deployment and the fore main velocity. So this is the height, sorry, the time of descent from when the main deployment happens. So main deployment to ground hit is what this time is, and then we'll take the drogue later and add those two together. So we also did a drogue parachute calculation. So this is a range from 12 inches to 48 inches for drogue chute size. And then we did the same thing, drogue area, since we used the same drogue area for the fore and aft, I didn't need to have more than one like I did up here. So it's all just one big thing. So the main velocity of the fore for a toroidal, or the velocity for an elliptical parachute. So we did use both. We ended up going with both elliptical parachutes for the drogues for a couple of reasons that, we'll see later, but the elliptical parachutes just overall are a better choice for a drogue chute. And you don't really find elliptical or toroidal parachutes that are so small. They don't usually make them that small. So we also had a parachute on the payload, so we had to do calculations for the payloads parachute. So this just is the same general idea as the last three. And we're just finding the main velocity of the payloads at landing. So now we have to calculate all of our kinetic energies. The kinetic energy is pretty easy to calculate. It's just 1/2 times the mass times the main velocity squared. So we had to calculate the kinetic energy of every single section. So we have the fore section and aft section, and then the fore and aft under drogue, and then the payload and nose cone and coupler, and then nose cone and coupler under drogue. So the payload only has one because it's under the drogue chute. It's just within the fore section. It stays inside there during that time. So it's not, it's only using its parachute after the main has deployed. So to find our drift, that's based on wind speed. So we had to do wind speed of 0 to 20 miles per hour was the requirement from the competition. And so this is a calculation that was done after these ones have been done. So you can see here I used T42. So this is up here, the time of the fore section. This ends up being a vector because this is a vector, right? And so I'm using the second one here, which is the 6-foot parachute, right? That 72 inches. And then the other one I'm using 6, which I believe is a 10-foot parachute. So those are the sizes we ended up going with. And so then this just calculates what the descent time is, the average time of descent for I guess a 5-foot parachute. So then we take the wind speeds and convert them to feet per second, and then put them into a vector. So we make it into a vector that we need, and then calculate the drift from that vector by multiplying it by this wind speed. So we just have to convert this vector into a different direction, basically, right? So we're calculating this one descent time multiplied by all of these wind speeds to find what the drift is for all of those wind speeds. And then for time of descent under drogue, right, this is the same thing that we did before, right, where we just have the height of the drogue minus the height of the main divided by the velocity under drogue. And then the total drift, so this right here is the drift just under main, right? But we need the drift under drogue too. So we do the same thing that we did up here, but for the main chutes. And then we have a payload descent time, which is just the height of the payload divided by the payload's velocity. And then the drift of the payload it's the same as up here, right? We just take the time of descent for the size of parachute we wanted to use. We significantly overestimated the size of the parachute for that one because we didn't need to use a smaller parachute. We could use a much larger parachute and we wanted the payload to stay safe. So we used a larger parachute than we needed because it was still within the descent time. So, and then we just convert it to a vector and multiply it by the wind speed. And then so our overall descent times in drift is we just add the drift under drogue and the drift under main for the fore and for the aft. And then the same thing for the payload, right? Because it has to drift, it still drifts under drogue even because it's within the body. So it drifts however far the body drifts. And then the final drift is just the drift under fore and the drift under main added together. So these are the total time of descents and these are the total drifts and then the payload drift. So to make sure that this code was accurate and was a good representation of the project, we did simulations in other programs as well. So we did OpenRocket simulations and RAS-Aero simulations, and then took the information that we got from those simulations, which was the velocity. So we got a landing velocity from both of those simulations, and then calculated the kinetic energy for each section at landing based on that velocity. So that's what these values are. And then we just compared that to the kinetic energy that we got from this Matlab code. So this code produces a ton of plots. Some of them are very useful and some of them are not so much, but they were, maybe useful one time and that's why it's in here. So first we have the chute diameter versus the time of descent from main deployment, and the chute diameter versus kinetic energy, the toroidal drogue diameter versus velocity, elliptical drogue diameter versus velocity, kinetic energy under drogue versus diameter under drogue of drogue parachute, the payload parachute diameter versus time, the payload kinetic energy, the chute diameter versus time of descent from main deployment, and the kinetic energy at landing versus diameter of main parachute, and the kinetic energy under drogue versus diameter of drogue parachute. And then we have a ton of things that are going to come up in the command window once we're done. So this is all of the answers that I want printed. These top three here, let's just look at them. So this is how we decided originally, right? So this is the main parachute diameter versus the aft kinetic energy at landing and the fore kinetic energy at landing. So I have, if I look at this, I can tell that I need it to be at least 10 feet, right? Because it can't be 9 feet because that's above the 75 foot-pounds requirement. And if I look at the fore section, any of them work, right? The fore section is much lighter than we anticipated, and so any of these ones will work. And then the drogue parachute diameter, it's all about timing, right? So time to main with an elliptical fore drogue. I need it smaller rather than larger because it's a 90-second requirement. And then time to main deployment with an elliptical aft drogue. There's the times there, right? And then this one was the one that was the biggest, is the wind speed. So we needed to make sure that this number never went above 2,500, right? Because the other numbers with the lower wind speeds aren't going to be higher. So these three here, the total drift rows, this one was the biggest, right? Because the aft section weighs the most, and so it was going to drift the furthest. And so with the parachute size that we chose of a 10-foot diameter parachute, it stayed below that 2,500 requirement. So the other things that it posts out here is the total time of descent for the aft section, the fore section, and the payload. As you can see, all of those are below 90 seconds, which is great. This is the velocity of the nose, or of the various sections at landing. And so, so that's an important thing to know. And then that also helps us to find the kinetic energy at landing, which, if you look at these, the closest is the aft section, right here, and it's still well below 75 foot-pounds, right? And according to OpenRocket, the highest kinetic energy is the aft section, and it's 71.4, which is much closer than this 62.2, but it isn't above 75. And then the kinetic energy based on, oh, that's supposed to say RAS0, sorry. The kinetic energy for RAS0 is still much lower than that 75 foot-pounds. So, and then I will show you guys all of the plots. So here is the for time of descent from main deployment versus diameter of the chutes. This time up here is the requirement, the 90 seconds, but this descent time is not super helpful, right? Because it's the diameter of the drogue parachute, or of the main parachute, but it's only descent time from main deployment. So this would be, about half of the, if not less than half of the time. So figure 2 here. Kinetic energy at landing versus diameter of the 4 main parachutes. So this shows us the same thing that was in this table up here, which is that, right, I'm well below that 75 foot-pound requirement with all of the 4 parachutes, and with the aft parachute, I'm really close at 9 and just below at 10, right? So I need that 10-foot parachute. Okay, and then figure 3 is what the velocity is with that toroidal drogue, and what, so this is the diameter of a toroidal drogue and the velocity of the body. And then the same thing, but with an elliptical drogue. And you see there's really not that much of a difference between the two of those. And then the 4 kinetic energy under drogue versus the diameter of the drogue chutes. So that's just what the kinetic energy is at under just the drogue parachute, which you can tell is very, very high, but that's because the main hasn't deployed yet. So this is payload time of descent versus diameter of payload. So there's a very linear correlation between how much time it takes and what size the parachute is. We ended up going with a 3-foot parachute. Actually, I think we may have switched to a 4-foot parachute because this 24 seconds was well within the payload descent time. And so it made more sense to try and keep our payload as safe as we could, because it couldn't take as rough of a landing as the rest of the body. So here's the payload kinetic energy at landing versus the diameter of the parachute. So, with that 4-foot parachute, the kinetic energy is very small. So yeah, the payload is not going to get damaged. So this figure shows the time of descent under the drogue versus the diameter of the drogue chute. So this paired with the time of descent under main shows the full time of descent. So, but it also shows that, with the really, really big drogue, we would be hitting that descent time just under drogue, which, we would not be able to do. The nose cone kinetic energy at landing versus the diameter of the 4, and then the same for the coupler. So this just shows what size parachute we need to stay within that kinetic energy at landing for the 4 section and, for the nose cone and the coupler. And then
thanks for watching, you guys.
The nose cone kinetic energy under drogue,
if you have any questions,
right?
please
So
put them in the comments.
that line is there to show the 75 foot-pounds, even though that is not a requirement for under drogue. The drogue kinetic energy is going to be very high. So when that main deploys, it slows the rocket down significantly. This is the code to calculate the descent time, the drift radius, the kinetic energy at landing, and to make a final decision on what size of parachute to use for our competition rocket. So I hope that this has been very helpful. If you have any questions, I'm more than happy to answer them.